Okay, so it's now recording. So are you set there, Nigel? I'm going to turn my camera off.
Yeah, I'm all set.
And I'm going to turn my mic off. So as they say, number one, over to you.
Right. Well, good evening, everybody, and welcome to another Maths Skills webinar. And this is all about time and how we determine time using the sun. So this is very much related perhaps to observational skills that you might be looking at, but it's also featured very strongly in the GCSE astronomy examinations. So let's get on having a look at time. 4 things to look at today. Just a few ideas about what time is and the basics of time. The other 3 are really all lumped together. How we use shadow sticks and sundials to determine time, how we correct it to where we are and what the date is using the equation of time and longitude. So it's quite an involved topic, and it involves a few numbers and being certain that you're aware of things like the angles spun by the Earth in particular in given time intervals. So let's get straight into the very basics. Now, what we know as time intervals, like days, years, and months, very much have their roots in astronomy. 1 day is the time taken for the Earth to rotate on its axis. Now, I'm not going to distinguish between a solar day of 24 hours and a sidereal day of 23 hours, 56 minutes. That's something else that we looked at, I think probably very early on in the course of webinars. So we're just going to call it a day for now. All right. It doesn't matter whether it's 24 hours or 23 hours, 56 minutes. It depends on really the sort of topic that we're dealing with. So the Earth rotates on its axis in 1 day. It orbits the sun in 1 year. Yeah, the Earth actually moves around the sun, goes around in an ellipse, which is almost a circle. And I used to say to my students, you see the sun up there? And they say, yeah. I said, well, 6 months ago, we were on the other side of it. It's difficult to think they were actually orbiting the sun sometimes because, you know, all the sun does is appear to rise in the morning and set in the evening. So the year, 365.25 days, but the year is based on the time taken for the Earth to orbit the sun. And the time taken for the moon to orbit the month, to orbit the Earth rather, is round about a month. Now, months can vary, you see, between 28 days and 31 days. So we've got a little complication there with our calendar, but more or less, the moon orbits the Earth in just under a month. I mean, month is a corruption of the word moon, a month. So there we are. Now, as I said, it's really important that you can relate time intervals to angles. And by angles, I'm talking about things spinning on their axis, like the Earth and the moon, and lines, imaginary lines that we met in Kepler's second law. An imaginary line from sun to planet sweeps out a given area in a given time. Well, it's that imaginary line, say between the Earth and the sun, that is going to be important. Okay, so let's just take this a little bit further on. Some useful facts here. Now, we know that in a complete circle, you'd have done this in geometry at school, whether you are still at school or whether school is a long distant past like myself. There are 360 degrees in a circle. Now, if the Earth orbits the sun in 365 days, then that means that in 1 day, the Earth, the imaginary line between the Earth and the sun, moves through an angle of just 1 degree, just under 1 degree. In fact, it might be, I don't know if anybody knows, I think it's lost in antiquity. But it might be that 360 degrees, which has lots and lots of factors, 2, 3, 4, 5, 6, 8, 9, 10, 12, 15, and so on and so on, was chosen as the number of degrees in a circle because it was close to 365, which was known to be the number of times, the number of days in a year. I don't know, but it's interesting. So the Earth moves through about a degree in its orbit in a day. A line between the Moon and the Earth, so the Moon's orbiting the Earth rather more rapidly. In a day, the Moon strikes out about 12 degrees. So that's why the Moon does tend to appear to have moved from one night to the next. So just the other night, it was just above the houses across the road. And then last night, it was much higher and much clearer. And it had moved by about, so this is from west to east, about 12 degrees. I didn't get my protractor there, but there it is, about 12 degrees per day. Now, coming on to time and how we determine time on Earth, the next little bit is really important. So the Earth rotates 15 degrees in 1 hour. Okay, so if you're looking downwards on the Earth and you had an imaginary protractor, the Earth will rotate by 15 degrees in an hour. So that means that it takes to rotate by 1 degree 4 minutes. And it's quite simple sums to work it out. But hang on, these students aren't quite sure there. I think they're selling me. I've gone a little bit too quickly there. So let's just explain this a wee bit more. Right, the Earth rotates by 360 degrees, one complete rotation in 24 hours. Now, as I say, I'm ignoring the 23 hours and 56 minutes. Let's keep it at 24 hours. Makes the numbers easy. So 360 degrees in 24 hours. Now, 1 hour, in 1 hour, that's a 24th of a day, isn't it? 1 hour is 1/24 of a day. So in 1 hour, the Earth spins through a 24th of one complete rotation, which is 360 degrees. And that equals, if you divide 360 by a 24, you get 15 degrees. So in 1 hour, the Earth spins through an angle of 15 degrees. This is nothing to do with its orbit around the sun. This is the Earth just as a separate object spinning on its axis. So it rotates in 1 hour by 15 degrees. And of course, stars appear to move westwards by 15 degrees of right ascension in 1 hour. In fact, 15 degrees is known as 1 hour of right ascension, isn't it? Anyway, let's not worry about coordinate systems. 1 hour is 60 minutes. So if the Earth spins 15 degrees in 1 hour, 15 degrees in 60 minutes, how long is it going to take to rotate through 1 degree? Well, we divide the 60 minutes by the 15 degrees and we get 4 minutes. Right, good. So the Earth spinning through 1 degree in 4 minutes, and maybe slightly less important, the Earth spinning through 15 degrees in 1 hour are going to be very important later. But it's that 1 degree in 4 minutes that we are really going to focus on. Okay. A question, or rather 3 questions. Let's see if you can work this out. Just to get the idea between angles and time intervals. So how long does it take the Earth to spin through 180 degrees? So that's half a revolution. Through 7.5 degrees, which is actually half of 15 degrees. You get these kind of magic numbers with this topic. And then through 1 degree. So how long does it take? How many minutes or how many hours does it take the Earth to spin half a complete rotation, so 180 degrees, 7.5 degrees, and 1 degree? Right, let's have some answers. Well, the first one, Should be 12 hours. There we go. Or if you're really being fussy, 11 hours, 58 minutes. But we're not, so we'll ignore that. 12 hours. 7.5 degrees is half of 15 degrees. And 15 degrees we equated to 1 hour, 60 minutes. So 7.5 degrees is 30 minutes, half an hour. And then 1 degree, of course, just to iterate, 4 minutes. By the way, as usual, I'm giving you the correct abbreviations for the units. We see hours abbreviated to HR quite a lot, but in science, they are H. And minutes are abbreviated to min, not mins, min. All units are really, should be given as singular. We say that as plural, minutes, or mins, but we write it as min, 30 min, 4 min, 12H, 5S for seconds. There we go. Right, well done if you've got those correct. So let's now have a look about how we determine time. And as it says at the bottom, the relationship between the two is very important, not only in finding the time, what the time is if we don't have a watch or a clock, but how we determine longitude, because it's not always been possible to determine that very important quantity, especially on board a ship. And knowing where you are on a ship is really rather important. But there was a big problem in the sort of 18th century in determining longitude. And we'll touch on that a little bit later on. Well, before we had clocks working on kind of different mechanical devices like pendulums and springs oscillating, now we use oscillations of crystals, little vibrations of crystal. But before all these, time, as you and I know it, not by the stars, but civil time, we used to use the sun and the special device called a sundial. Now, all a sundial is really is something that casts a shadow. In fact, it's got probably one of the most strange names in astronomy, a gnomon. So that triangular thing you can see on the base there is the gnomon. And the slanted part, the shiny part there, you can see, points to the North Celestial Pole. And as the sun swings round from east to west, and as the sun gets higher in the sky before noon and lower in the sky after noon, the shadow makes or intersects a different mark on the dial, as it's called. That scale is called a dial. So we have a sundial. Works brilliantly in the daytime if it's sunny, doesn't work at night, doesn't work in cloud. You really need full sun. So there is a nice simple sundial. You might have one in the garden. You might have one in the local park or a local churchyard, something like that. Now, with a lot of terminology and a lot of abbreviations, what I'll try to do is to make it simple so we don't have too many abbreviations. I'll try to give them as the real names. So when you read a sundial, you read the apparent solar time where you are. That's where the local bit comes in, because apparent solar time differs from place to place. So the time given on the sundial is apparent solar time. So you read off where the edge of the shadow is on the scale and you read a time. And that's your local apparent solar time. Now, that doesn't give you real time, time that you might have on a watch or a phone or the town hall clock or a railway station. And there are two reasons why. There's something weird called the equation of time that actually means the correction to time, which is far more sensible. And also, you may well not be on the prime or Greenwich meridian. And both of these factors cause the time that you read on a sundial to be incorrect. So how do we know what the real time is? Well, we've got to move on. Now, it's going to be useful to think about the sun moving across the sky from east to west. Never mind it rising and lowering as well. Let's just have it moving across the sky and moving by, about a degree in 4 minutes, as we've said. Now, it doesn't move every day in the same manner. It's not like a pendulum that you let go and it will tick, 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 and so on at the same time interval all day long. The sun doesn't do that. And there are two reasons why it doesn't. And they're both to do with the Earth. We're observing the sun from the Earth, so it's variations in the Earth's motion that cause the sun to appear to move differently. Now, the first thing is that the Earth orbits the sun in an elliptical path. Kepler's first law, it's not that far from a complete circle, but it's far enough. So it orbits an elliptical path, and so its speed varies. And that was Kepler's second law, remember. So when it's closest to the sun in January, it moves quickest. And when it's furthest from the sun in July, it's, is it that way around? I forget now. Anyway, the Earth moves in an elliptical path, so its speed changes. Yeah, it's faster in January and slower in July. That's right. The second reason why the sun doesn't move in a regular manner is that the Earth's axis, as you know from the first webinar about the Earth and the axis, is tilted to the plane of its orbit by, 66.5 degrees, isn't it? So the Earth's axis is actually tilted to the plane of its orbit by 66.5 degrees. So both of these mean that the sun doesn't move in a regular manner. So what we've got to do is to invent a mean sun, an imaginary sun in the sky that moves across the sky every day at the same rate. So every hour it moves westwards by 15 degrees, not 14.7 or 14.8 or 15.2, always by the same amount. Okay, so moving across the sky every day at the same rate at the bottom of the page there means that it travels, it sweeps out the same, it travels through the same angle every hour, every day. So it's a kind of perfect sun. And the difference between the time that the sundial tells us and the time that we can determine using the mean sun is called the equation of time. As I say, its more correct name is a correction to time, because you use the equation of time to change sundial time into mean time, which is the one that we use for timekeeping. We don't want days and hours of different lengths because the sun moves slightly faster across the sky because the Earth's actually moving faster in January, do we? We want the same length of hours and days as we do on a watch or a clock. And that uses this mean sun. Okay, so it's not real. The real sun gives us time by the sundial, and we have to correct it to the mean time using the equation of time. There we go, and there's the formula that is in the book there. So the equation of time, EOT, that's an easy one, is the apparent solar time, so sundial time, take away mean solar time. So you can rearrange that and get the mean solar time equals the apparent solar time, take away the equation of time. So what we've got to do is to think of two suns in the sky. So whenever you see the sun in the sky through sunglasses, or when it's setting, think that's the real sun. There's also another one that's slightly in front or slightly behind. But you can't see it because it's not really there. But it's really, really useful in astronomical timekeeping. Okay, so we've got the real sun that gives us shadows. And we've got the imaginary or mean sun, which is a few degrees ahead or behind the real one. Now we can show this very nicely graphically. Here's a graph showing the equation of time. Now we did charts and graphs last week. And I think the first thing that I said was make sure you're absolutely sure what the axes are. Well, the axes along the bottom are months. So we've got the month of January, February, March, and presumably we've got 0 up to about 30 in those little boxes. And then up the side, we've got the sundial time, that's apparent solar time. Take away clock time, which is mean solar time. So up the left-hand side is the equation of time. And it varies between plus 18 minutes and minus 16 minutes. So the real sun can be ahead of this mean sun by up to about 17 minutes, and it can lag behind by about 14 minutes. Because when there's a dip, when the equation of time is negative, it means the equation of time, well, it means really that the sun, as we see it in the sky, is moving slow. It's slower than it should be, so it's behind the mean time. So we've got a big dip, a little rise, a little dip, and a big rise. You do see other versions of this, but this is the correct one for GCSE astronomy. Now, there's another one that we call an analemma. I call it a wobbly snowman because it looks like a snowman that's wobbling to the side. Now, this takes a bit of sorting out. You could be given one of these in the exam and be given a date, or you could be given an important time, like the sun is passing the equator, all right, moving from kind of northern to southern hemisphere. What's the equation of time? Rule. All right, so this time the equation of time is along the top, and it's positive on the left and negative on the right. So when the sun is fast, can you see at the top there, sun fast, that means that the equation of time is plus 60 minutes, 40 minutes, and so on. When the sun is slow, then the real sun is behind the mean sun, and the equation of time is negative. So it should actually be on the right-hand side there at the top, -2, -4, -6, and so on. And then it gives you dates of the year, or it gives you important declinations of the sun. Either of those, you can read off the equation of time. And you can see that on 4 dates, the equation of time is 0. Can you see that? Going up to the top from 0, coming down, June the 13th, coming further down, April the, let's get that right, about 16th. No, April the 20th, sorry, and then April the, no, August then, isn't it? Ooh, crumbs, it does take a bit of sorting out. This is a very small picture on my screen. August the 29th, something like that. And then, funnily enough, Christmas Day, 25th of December. So that's an analemma. That's a different version of the other, let's put that back up, equation of time graph. You could be given either of those and asked to work out the equation of time. Remember, it's a correction factor. All right, it's nothing weird, the equation of time, it's a correction factor. It allows you to work out your mean solar time from your apparent solar time. So here we go, a nice example. So once you know the equation of time on the date when you are observing with a sundial, you can find your mean solar time, not your apparent solar time. That's the one that you read on the sundial, your local mean solar time. And just to confuse things, mean solar time is also known as local mean time. I prefer to think of it as local mean solar time, but you don't find that abbreviation LMST very much. So let's have a look. If your sundial reads 10:30 in the morning and the equation of time is plus 8 minutes, what will your mean solar time be? Well, the mean solar time is the apparent solar time take away the equation of time. So that's the formula for the equation of time earlier, just rearranged, a bit of algebra there. So MST, the mean solar time, is the apparent solar time, which is the time on the sundial, 10:30. Take away the equation of time, which is 8 minutes. So 10:30, take away 8 minutes is 10:22. So your real time where you are locally is 10:22. It's not 10:30 at all. Let's do another. Oh no, I thought there was another one. There's not. Right. Okay. There's some more examples a little bit later on, so we'll get our heads around that. Now, once you found your local mean solar time, it still won't agree with the town hall clock. Lovely image there of Bolton Town Hall. I know it well from my younger days. The town hall clock or your watch or your phone will not agree with your mean solar time, because they give the mean solar time in Greenwich, not where you are. Up to about the beginning of the 19th century, when railways were starting to take off, every town, every city had its own local mean time. And it was very confusing, especially if you had trains and timetables. And there are tales of saying you could start off on a train in one place and end up in another place actually earlier than when you set off. Now, I think that's a bit of an exaggeration myself, but it was chaotic. So everybody agreed, well, not everybody agreed. Some mayors of cities really objected to this, but it was made law that everybody should use the same time interval in our kind of time zone. And that was the time, the mean solar time, based in Greenwich in London, where the Greenwich Meridian is. So once you've got the local mean solar time, as we've just looked at, you've then got to calculate how many degrees and east and west of Greenwich you are, because then you need to add or subtract 4 minutes. So if you're 1 degree of longitude, east or west of Greenwich, you add or subtract 4 minutes. If you're 2 degrees, you add or subtract 8 minutes. And that's the time taken for the Earth to rotate through 1 degree. Now, the next bit I find really difficult. Do we add on or do we subtract? Well, let's have a look. If you're 1.5 degrees west of Greenwich, and the nearest big town I could find, or is it a town or is this a city? I think it's still a town, in Reading. So you're west of Greenwich in Reading. You need to add 6 minutes. So in 1.5 degrees, that corresponds to the Earth rotating. Okay, in 6 minutes, you add the 6 minutes to your local mean time to obtain Greenwich Mean Time. And that is civil time. And that is the time on your watch, on your clock, or the town hall in Reading, Bolton, or anywhere in the local time zone. So even in Dublin, in the Republic of Ireland, even in Reykjavik, in Iceland, they're in the same time zone. So you can actually find the Greenwich Mean Time in those places as well, because it's the same as that in London. So Greenwich Mean Time is local mean time. That was the 10:22 plus 6 minutes. So Greenwich Mean Time. So we've looked at our sundial and we've read a value, we've corrected it for the equation of time, and we've made another correction in the fact that they're 1.5 degrees west of Greenwich, and we've got the time, 10:28. Isn't it simpler to look at a watch or the town hall clock? Well, unfortunately, a long time ago, this wasn't possible. And people had to use sundials and use the equation of time and then add on. Well, no, they didn't need to add on or subtract 4 degrees east or west of Greenwich, because that was their local time. It was only really when the, what's it called, the Railway Act or something like this, made it a law that we would all use the same local mean time, that in Greenwich. Now, this is the difficult bit, and this is why I've got this graph here. Do we add on or do we subtract? Okay. Now, what we've got here is a map of the south of England and northwest France. And let's assume that in Greenwich, in London, it's 12 noon. Okay, so that's the local mean time in Greenwich, and it's also Greenwich Mean Time. It's the time on every town hall clock that you can see on that map there. Now, let's go to Bournemouth, okay, 11:52. It's 8 minutes earlier in Bournemouth than it is in Greenwich. Because if you can imagine that this map is moving, is rotating from left to right, the sun is actually moving from right to left, isn't it? The sun's actually moving from right to left. So you can imagine an imaginary sun just moving across from right to left. So if it's 12 o'clock noon in Greenwich, it isn't noon yet in Bournemouth because the sun hasn't reached there. It's still 11:52. So that's why if you are west of Greenwich, you add the number of minutes, and if you're east of Greenwich, you subtract, because we've already got, look, in between Calais and Dunkirk, it's already 12:08. So in Greenwich, for the real time, we've got to take away 8 minutes. This needs studying quite a lot. This is not easy. We'll come to that graph again a little bit later on, I think. There we go. So it doesn't matter where you are in the UK, or whether you're in the Republic of Ireland, or Iceland, or Portugal. I think those are the only European countries, quite a few in Africa as well. These are all located in the same time zone, and therefore all the clocks and watches and phones are in good agreement with each other. So before we had all this modern technology, it really was quite a faff, wasn't it, to determine time? Can't ask somebody in the road, what's the time, please? Somebody look at their watch and say, oh, it's 11:30. They would have to go to a sundial, use the equation of time, realize where they were, east or west of Greenwich. All right. Subtract or add 4 minutes for every degree. So about 5 minutes later, they'll say, oh, it's 11:56, and you'll have missed your bus by then. So now, the important thing is a kind of converse of what we've just been talking about, because you can now use your local mean time and local mean time in Greenwich, GMT, to determine longitude. And this is the principle by which you can determine your longitude at sea if you don't have GPS and things like that. And this is one of the projects that you can attempt for your observational skills. And it's one I highly recommend. You could maybe do this on 2 or 3 different days. You just need a sunny day. Well, we've got some sunny days at the moment, I think, haven't we? For quite a while. Maybe different sunny days when we've got a different equation of time. So maybe now, maybe in September, maybe, one of these short sunny days in early December that we tend to get. So if you can find your local mean time where you are, which we know you can, and your local mean time in Greenwich, which we can work out, you can determine your longitude using this same idea of 1 degree corresponding to 4 minutes. And for this, you need a shadow stick, a straight stick about maybe 1/2 meter to 1 meter long, and you need to measure the length of the shadow every 5 minutes. There we go. 1 stick in a plant pot, 1 shadow, and of course the shadow will alter its position, and it'll get longer, and it will actually get shorter and then longer, depending on whether we are before noon or after noon. So the idea is to measure the length and record it of the shadow every 5 minutes from 10:30 to 1:30. So that's about 1.5 hours before and after noon. And you plot a graph of the length of the shadow against time. Now, I think we have this in our graph plotting last month, not last week, I made an error there, last month. We plot the length of the shadow against time. And we don't use as a 0 on the axis, otherwise that dip will be very shallow. It'll be more like a saucer. So we have a false origin on the, on both axes. So you put the crosses on, once you've got your table, and then you draw a lovely, nice, smooth line with your hand inside the curve. Okay, so it's probably best to turn your graph paper around a little bit, clockwise a little bit, and draw a nice, smooth curve. What you're looking for is the bottom of the curve and the time at Greenwich when that occurred. And I make that 11:58. Okay? 11:58. Each big square, no, 11:52, sorry, 11:52. Can't read my own writing there. Each big square is 20 minutes. So, yeah, there we are. I think this data was recorded every 10 minutes, not 5 minutes, which is perfectly adequate. That's not a problem at all. Right. So Greenwich Mean Time, when the shortest shadow occurred, so local mean time in Greenwich was 11:52. Right, remember that if you can. Now, when the shadow is shortest, the sun is highest in the sky. Okay, its altitude is greatest. So obviously, local apparent solar time, we don't need a sundial for this, is 12 noon. By definition, apparent solar time, time as measured by the real sun, when it's highest in the sky, it's due south, and it's 12 noon. Not 12 a.m. or 12 p.m., by the way, they don't exist. 12 noon. Well, like before, we can use the equation of time to convert the apparent solar time of 12 noon into mean solar time or local mean solar time. I'm giving you both in the brackets. So let's say on the day we carry this out, it's minus 10 minutes for the equation of time. So your local mean time is the apparent solar time, 12 noon, take away the equation of time. So it's 12 noon, take away minus 10 minutes. All right, so those two minus signs, one's a take away sign and one's a minus. And what happens is that they become a plus. So if you take minus 10 minutes from 12 noon, you get 12:10. And that is your local mean time. Okay, double negative. 12 o'clock, take away minus 10 minutes. So watch those two minuses next to each other. I put a bracket round just to highlight that. And we've got a local mean time of 12:10. All we need to do now is compare that local mean time to the local mean time in Greenwich, which was 11:52. And I think you'll agree that the difference between 11:52, let's just go back, and 12:10 is 18 minutes. So the difference in local mean time where you are and the local mean time in Greenwich is 18 minutes. So how much has the Earth spun? 18 minutes. Well, it's 4 minutes for 1 degree. So we divide 18 minutes by 4, we get 4.5 degrees. So we've used our shadow stick to determine that our longitude is 4.5 degrees east or west of Greenwich. All right. Now, our local mean time was 12:10. And time in Greenwich was 11:52. So, by the arguments earlier, we are east of Greenwich. We're somewhere in Holland, I think, because our local mean time, 12:10, is later than Greenwich. So if our local mean time is later than Greenwich, we're east. If our local mean time is less than Greenwich, the sun hasn't reached us yet, and so we're west of Greenwich. There's that little chart again. It's not an easy topic. This is why we do it as a topic in the normal webinars, and also a special one with these math skills. All right, so these keen students would like to try some for themselves, which means you can have a go at about 4 little questions here. So we're in Oxford and it's sunny and we've got 2:30 p.m. on our sundial in Oxford. Now the equation of time for the day when we're doing this, it does vary slightly from day to day. Not in an irregular manner as you saw from the graphs. So what's the local mean time in Oxford? So there's no equation of time. Sorry, there is an equation of time of 6 minutes. And we're not interested in the longitude effect because we want the local mean time in Oxford, not the local mean time in Greenwich, not Greenwich Mean Time. And the answer is 2:24. So the mean solar time, or the local mean time, is the apparent solar time, take away the equation of time. So take 6 minutes away from 2:30 to get 2:24 in the afternoon. Okay, another one with a negative equation of time this time, and this time we're in Cambridge. Lots of sundials in Cambridge. What's the local mean time in Cambridge? Well, the local mean time is the apparent solar time, 11:45, minus the equation of time. It's one of these double minuses again. So we should have 11:57. There we go. Right, let's complicate things a little bit, just slightly. Let's say we're on a day, let's say we're on Christmas Day, when the equation of time is 0. And the shortest shadow cast by a stick occurs at 12:04 p.m. That's just after 12 noon. Okay, it's not late at night, it's 12:04 p.m. in the afternoon, early afternoon. Where did we carry this out? What was the longitude? Well, it's clearly 1 degree, but apparent solar time is 12 noon, and mean solar time at Greenwich is 12:04. So we're earlier than Greenwich, and therefore we're 1 degree west. All right? And then just to finish, let's have an equation of time. You might have to jot this one down. The equation of time is plus 2 minutes. The shortest shadow cast by a stick is at 11:52. Now you don't do anything to that yet. You work out the mean solar time. So it's 12 noon, take away 2 minutes, 11:58. So the local mean time in Greenwich, according to your watch and clock, was 11:52. So I make that 6 degrees difference. So that should be 1.5 degrees. Oops, I've made it 2 degrees. What have I done there? I've done 12 o'clock, take away 2 is 11:58. And I've assumed that that is, for some reason, I did check these twice, is 8 minutes. It's not, it's 6 minutes, isn't it? So it should be 1.5 degrees. And again, it's east because our mean solar time is later, 11:58, than that at Greenwich, 11:52. So that's 6 minutes. Silly me. Apologies for that, everybody. 1.5 degrees east, that should be. Well, I said it was tricky. I said it was difficult, and it is. There's a lot to remember. Good. So if you want more practice for these, there is a whole section on longitude and time on the Essential Math Skills resource. that you can get directly from myself, should you wish to. But for now, thank you so much for participating, for joining us this afternoon. And we're looking forward to seeing you perhaps in a week's time or perhaps in a month's time for our next astronomical math skills webinar. So have a good look at the numbers, double check the numbers as I did, and I can still make a mistake. So that just goes to show it's quite easy to just make a little slip. So 4 minutes, 1 degree, 6 minutes, which I took to be 8 minutes for some reason, 1.5 degrees. Good. Okay, thanks very much, everybody. That concludes the session today. Let's see if there's any comments or queries.